All right, so today we're going to be looking at the 2000 USNCO local exam, and we'll just be going in order. So number one, which metal reacts most vigorously with water? Here, you can divide your answer choices into two different types. So there's alkaline earth metals and then there's alkali metals. You want to eliminate the alkaline earth metals because we know that alkali metals are the most reactive metals on the periodic table. And then how you decide between potassium and sodium is by looking at their placement. So potassium is below sodium. So that means it's got an extra shell on it, which means its valence electron is going to be further away from the nucleus. So it's going to have like less attraction because the distance is further, and it's going to be easier to, if you can think about it, like pluck off that one valence electron. So that's going to make potassium more reactive than sodium. And I know I just explained it like kind of lengthily, but you could just think about it as ionization energy trends. Okay, which substance produces an acidic solution when it is bubbled into water? So you kind of just want to classify each answer choice here. When this is bubbled into water, you get carbonic acid. Argon is unreactive because it's a noble gas. And then these two are bases. So you want to cross out your bases because obviously they're not going to produce acidic solutions when you're bubbling them into water. Argon, like we said, is unreactive, so nothing's going to happen. And then carbon dioxide, when you bubble that into water, like we covered, it's going to produce carbonic acid. Okay, which substance is least soluble in H2O? So we know that any alkali metal cations will make the compound they're insoluble. So you can cross out potassium carbonate and potassium bicarbonate. So now it's just a debate between the two calcium containing compounds. And you can actually just cross out calcium bicarbonate as well, because most bicarbonates are going to be soluble just by solubility rules. So that leaves D. One interesting thing that you don't need to know for like this problem, but it's like kind of tangentially related, is that we covered that carbonates are like usually insoluble and bicarbonates are usually soluble, but for alkali metal compounds, so like let's say Na2CO3 and NaHCO3, obviously these are both soluble, but the carbonate is actually more soluble than the bicarbonate. So since this question is asking least soluble, if you ever had to compare for like alkali metal carbonates and bicarbonates, then you know the trend. Okay, what value should be reported for the Barrett reading? So whenever you're like reporting a value based on like a measurement, you want to go 1 degree of precision past what the instrument tells you. So this Barrett is reading in tenths of a milliliter. So you need to report to hundredths of a milliliter. That's not a 3. That's just me showing like the distance between each tenth. So obviously this one is the only one reported to the tenths, so that's wrong. And then if you look at the bottom of the meniscus, it's like in between 22.3 and 22.4. Try to draw like a horizontal line. So that hundredths place digit is just kind of a guess. So you can put whatever you want, but it's definitely not 0 in either case. So it's C. Okay, number 5 is just kind of common sense. Just like put yourself in that situation and deem what is safe in the lab. So sniffing a test tube right under your nose, not a good idea. Transferring the liquid to a desktop, not a good idea because you're still gonna like be sniffing the thing. Sniffing, no. So D is right because this is always what you want to do when you're dealing with chemicals with odors. You want to be wafting and also like not wafting too much either, because you only need a little bit usually to get to be able to identify like what something is if it has a really distinct scent. Okay, so 6 has to do with qualitative analysis. So we're dealing with some kind of chloride compound. So we can get rid of Cu2 plus because that's a soluble chloride. And we're only dealing with insoluble chlorides here, which are called the group 1 cations. So those would be Pb2 plus, Hg22 plus, and Ag plus. So how we differentiate between these, or like see which one or like which ones of them are in solution, is first you add hot water, and that's what we did in this case. And if you have a precipitate that dissolves when the hot water is added, that means you have Pb2 plus in there because PbCl2 will actually dissolve at higher temperatures. That's not the case with AgCl or Hg2Cl2. And I mean, we solved the problem, but for the scope of just like qualitative analysis, I'll keep going. And then say you're left with like more chlorides in the solution, but you don't know like what is there, then you would add ammonia. And then if you see like the solution clearing up, that means that there was AgCl in there, because if you add the ammonia, you'll actually be creating a complex ion, which basically like dissolves the AgCl. And that looks a little bit like this. Cl minus, and these are both aqueous. So that's why the AgCl would dissolve. And then if you had ammonia, you would have that clearing up of the solution if you had silver chloride in there, or silver 1 chloride. And if you had mercury, then it would look kind of weird. So I'll just draw out the reaction. So HgCl2 by itself is here. That is white. But then if you add the ammonia, I'm just going to not write states for now, so it goes by a little quicker. You get just mercury, which is black. And then you also have this thing, which is white. And then you have ammonium and chloride just to balance stuff out. But basically what you'd see here is you go from a distinctly white, like solid, and then once you add the ammonia, stuff will turn black, and then eventually as the black and white mix, you'll get gray. So if you see like these weird color changes when you add ammonia into the solution, that's how you know mercury is there. And that obviously might cover up like the visibility part of this, because you won't be able to see if like the solution's clearing up, if it's turning like black and gray. So after you notice this happening, what you can do is add nitric acid to the solution in order to break up this complex ion. And then if you see reprecipitation of like something white, then that's AgCl. So that's like group 1 qualitative analysis. Okay, number 7, a student is asked to measure 12 milliliters of a liquid as precisely as possible. Which piece of equipment should she select? Okay, so precisely is all about like how many decimal places you can do something to. If you have good tools. If you don't have all good tools, then it's literally just like how close can you get? So if we just look, obviously like a graduated cylinder versus a beaker, a graduated cylinder is going to give you a more precise measurement. Same case with the conical flask. And then some people might get tricked by the fact that this says volumetric flask, because you might have dealt with like a volumetric flask, and you know that like has that line that tells you exactly like in this case what 25 milliliters is. But don't forget that we're measuring 12 milliliters, so we have absolutely no way to compare. So our answer would be the graduated cylinder. Okay, number 8, which separation technique is based on differences in the volatility of the substances to be separated? So filtration deals with densities, right? Because you just wait for like things to separate out into 2 or more different layers, and then you like turn the stopcock in order to like release one and then stop it when you have like your desired separation. So it's not filtration, because that has nothing to do with volatility, which is all about boiling points. Solvent extraction and paper chromatography all have to do with like intermolecular forces and what is it, like dipole, basically how substances interact with each other, which is once again not volatility. I was looking for the word polarity. So distillation is what's left, and basically there are different types of distillation, but all you have to know is that all types of them involve like boiling or like setting your setup to a certain temperature. So you boil one thing off, but not the other. And then you collect the other thing in a separate flask by basically you run the gas through like condenser tube that's like with cold water running around it. So it condenses the gas that you collected, and then you collect it as a liquid in the other flask. Okay, number 9, if you have this much oxalic acid, but not anhydrous, and you heat it off to drive off the water. Okay, so basically all you have to do is, I'm going to erase what's to the side right now. All you have to do is do some like stoichiometry. So you take the grams of what you have divided by the molar mass of like that thing. So there are 6 H's in total, right? So that would 6 times 1.008 is 6.048. There are 2 carbons in total. So 2 times 12.01 is 24.02. And there are 6 oxygens in total, and 6 times 16 is 96. So that gets you 0.0119 moles of this compound with the hydrates included. And then you drive off the water, and basically this times 2 is how many moles of water are inside that hydrate, right? Because like you have the coefficient 2 here. So that's how much water you're driving off. So if you multiply 0.0238 times the molar mass of water, you're evaporating 0.429 grams of water. And then that's about 0.43. So if we look, 1.5 minus 0.43 is 1.07. It's asking how much mass remains. Okay, how many H atoms are in 3.4 grams of sucrose? Kind of the same deal as the last question. You have to start with the mass and then find the molar mass and then get the moles and then multiply by a coefficient and then multiply by Avogadro's number. So here, I'm not going to do the mental math. I'll just write it out. Hold on, 22, 1.008 plus 11 times 16 grams per mole, which gets us something. All right, hopefully my calculator skills are good and I didn't just get that wrong. But 0.0099 moles of the sucrose, then we need to multiply that by 22 because there are 22 atoms of hydrogen in every molecule of sucrose. So times 22, that gets us 0.21, or I guess 22 here. I was going to write more, but the sig figs work out to 22. And then if you do 0.22 times 6.022 times 10 to the 23rd, because you're converting, what is it, molecules to atoms, or no, moles to atoms, then you get 1.3 times 10 to the 23rd. Yeah, all right. All right, so probably gonna stop here for this video, just 1 through 10, and then stay tuned for more later.